An 80-kilogram man is 1/4 of the way up of a 10-meter ladder that is resting against a smooth, frictionless wall. And if the ladder has a mass of 20 kilogram and if it makes an angle of 60 degrees with the ground, we are asked to find the normal force from the wall, normal force from the ground, and the frictional force by the ground on the base of the ladder. So let's start by visualizing the problem. I'm going to specify positive x to the right, positive y to the up. And I'm going to specify counterclockwise torque as positive. So let's look at the forces acting on the ladder. The friction force is acting here, and if there were no friction, the ladder would slip down and move out to the right. And friction force opposes the motion, therefore the force of friction points in this direction, and this is a static friction because nothing is moving in the system. And the weight of the ladder, it is at the center because we assume the ladder is uniform. Therefore, the center of mass is located at the midpoint of the ladder. So the distance should be L by 2. And the next force is weight of the person on the ladder. As it is stated in the question, the man is at 1/4 of the way up the ladder. So that distance should be 1/4 of the L. And the weight of the man on the ladder is acting downwards. And the next force is I'm going to consider. So there are two forces acting in negative direction: the weight of the ladder and then the weight of the man. So in order to balance those two forces, there should be another force acting in positive direction. So this is the normal force from the ground, and right here the ladder is not falling. Therefore, there need to be another force balancing the ladder. So there is a force from the wall acting to the right. This is the normal force from the wall. So these are the forces acting on the ladder. Now let's try to figure out the angles. So as it is stated in the question, the ladder makes an angle of 60 degrees with the ground, and if that is 60 degrees, this angle should also be equal to 60. These are alternate interior angles. When you have two parallel lines, you can consider the alternate interior angles, and they should be equal to each other. If that angle is 60 degrees, this should be 30 degrees because you can see it is a right angle. It's 90 degrees. And if that is 30 degrees, the angle here, the angle between the weight of the man and the ladder should be 30 degrees. Again, alternate interior angles. The weight of the ladder, weight of the man, force of normal force from the ground, all these three forces are parallel to each other. Okay, so then we have to look at the weight of the man. Weight of the man is his mass is equal to 80 kilograms times 9.8, 784 newtons. And then the weight of the ladder, so weight is equal to mass times 9.8. So 20 kilograms times 9.8, we get 196 newtons. Applicable concepts. So we know the system is at a static equilibrium. Nothing is moving. Everything is stationary. So that is the concept we are going to use here. And have we specified the coordinate system? Yes. And symbols of what we are trying to find: an expected sign. We are trying to calculate the normal force from the ground, the normal force from the wall, and then we are trying to calculate the static friction force. Normal force from the wall is acting to the right based on our system, so it's positive. Normal force from the ground is positive, static friction is to the left. negative. I'm moving fast here, and then the unit is actually newtons, right? All those forces are measured in newtons. So, okay, so let's plan the solution now. When the system is at a static equilibrium, we can use the net force in x direction, the component form of Newton's second law, in x direction, y direction, and then net torque is equal to 0. Okay, now let's execute the plan. Now, when we execute the plan, guys, we have to use the equation for the torque. And remember, whenever you calculate the torque, we have to choose an axis of rotation. We calculate the torque um, with respect to that point. So in my free body diagram, I'm going to go back and define an axis of rotation. I'm going to choose a point. You can choose any point on the diagram, but please be smart enough to choose a point that has a higher number of unknown forces. So I'm going to start that point because then the torque from the static friction and the normal force is going to be 0. So that is my axis of rotation. So once you have the axis of rotation, we have to look at the forces that creates a torque about that point. Normal force from the wall is going to create a torque, and then weight from the ladder is going to create a torque, and weight from the man is going to create a torque. So now if you consider about the torque created by the normal force from the wall, we have to see whether it is a positive torque or a negative torque. You can see this normal force from the wall is going to rotate the system clockwise. So that torque should be negative. And the length is the entire length of the ladder, the distance from the axis of rotation. So negative force times distance is L sine 60. And then the torque from the weight of the ladder, as you can see, it is going to create a counterclockwise torque. It's going to rotate your system counterclockwise, so that should be a positive torque. So force times the distance is L by 2 sine 30 degrees, and then torque from the weight of the man is also going to be positive because that force is going to rotate your system counterclockwise with respect to the axis of rotation, you can see. So I'm going to assign a positive sign for that torque, and then force times the distance is L by 4 times sine 30 is equal to 0 because the system is not moving. There's no net torque. There's no net torque. So now if you separate out the normal force, I think you will be able to follow how I have done here. I've skipped few steps. I'm just trying to separate out the normal force and write an equation for it. And this is what I get. And now we have done the difficult part, guys. We just have to do the substitution here. And we already know the weight of the ladder. We calculated it earlier. So before I continue the calculation, I'm going to cancel L because it's common for all the terms in the equation. So you can divide top and bottom by L. And then I have the weight of the ladder, 196 newtons, and then half times sine 30 plus the weight of the man is 784 newtons times 1/4 times sine 30. Divide that by sine 60. When you solve for the normal force from the wall, you will get 169.74 newtons. So that is a positive because it's acting to the right. We have specified right as positive. And now let's calculate the next unknown force. And I'm going to use the component form of the Newton's second law in y direction, since the system is at an static equilibrium. Static equilibrium means net force is 0, net torque is 0. The net force is going to be 0. In y direction, you can see there are 3 forces. You have to consider the weight of the ladder, the weight of the man, and then the normal force from the ground. Normal force from the ground is positive, acting up. The other 2 forces are negative. And the normal force from the ground is equal to weight of the ladder plus weight of the man. And we already did the calculation for the weight. Mass times 9.8 is the weight. And that would be equal to 980 newtons. Easy. And the next force I'm going to calculate is the static friction force. So the next option I have is obviously to use Newton's second law in x direction. And if you look at the free body diagram, guys, we have only 2 forces in x direction. One force is the static friction force, the other force is the normal force from the wall. And we know the acceleration in x direction is 0. So if that is the case, I'm going to go back to the diagram and show you the 2 forces. I'm sure you have this on your paper by now. You have the normal force from the wall and then static friction force. Normal force from the wall is acting to the right, it's positive. Then static friction force is acting to the left, negative, 0. And then normal force from the wall is already calculated. That was the first thing we did. We used the torque equation to calculate the normal force from the wall. And that's just equal to static friction force, 169.74 newtons. Okay, is the solution complete? Yes, is the sign of the answer correct? So static friction force is acting to the left. So I'm going to write it as acting to the left. I already accounted for the negative sign in the calculation. That's why I don't have the negative sign in the final answer. So I'm going to specify the direction. Everything is done, completed here. So just see the steps we followed. We have the free body diagram. We assume the object as a rigid body. When you draw the free body diagram, you have to show the entire length of the object. And then we use the Newton's second law